So it's my great pleasure to welcome Professor Sebastian Will from Columbia University, our neighbors. I don't know if you recall, but when I started at NYU, I'm behind Sebastian, but we did a lot of great things together. Even though our research is not completely aligned, we worked with Flatiron. We started something called Joint Quantum Seminars. We had this trial between Flatiron, Columbia, and NYU, and it turned out it's extremely fruitful. We moved on to our own directions. You will hear from Sebastian. It's fantastic what is happening there. But I'm really happy that we're kind of growing that community, and obviously right now what we have is nowhere near what we had before. Right? We were kind of lonely back there, but now it's a very good crowd in the community. So Sebastian is a professor of physics at Columbia University. His research is on ultra-cold atoms and molecules with a very direct focus on, I would say, quantum information science, quantum simulation, and really quantum computing. He also does quantum networking. I guess there are some phenomenal things that are happening that he will tell us about. Sebastian is a recipient of Columbia Rise Award and a Safe Career Award, a Sloan Fellowship. He's funded by every agency you can think of, NSF, A4SR, ARO, ONR, DOE, and also Gordon Betty Moore Foundation. So without further delay, welcome, and we're excited to hear from you, Sebastian.
Thanks so much, Javad. Well, thanks so much, first of all, for the invitation to come here. It's really great to be back. I mean, as Javad already mentioned, we go back a long time. I did a lot of fun things together. Then COVID came, and some things kind of developed in different ways. But we should revive keep
COVID was fun too, wasn't it?
What is that? What is that?
COVID was fun too.
Depends on how you see it. So of course we are having fun in the lab, no matter what, right? And I'm looking forward to tell you more about our work on creating and exploring Bose-Einstein Condensates of dipolar molecules. I also want to say throughout the day I had great discussions with faculty colleagues, but I also want to really acknowledge the great discussions with the students. This has been a lot of fun so far. And also in the discussions with students, the question came up, why molecules? So, people often ask me, why do you work with molecules in AMO physics? There is a saying that even a diatomic molecule is one atom too many. There's a lot of truth to it. And when people ask me why I work with molecules, I sometimes give a fancy answer and talk about quantum simulation and quantum computing. This is all good and whatnot, but actually, truthfully, I'm motivated for this research with molecules for a different reason. Basically, in the last 100 years, concurrently with the theoretical development of quantum mechanics, there has been a continuous effort to bring more and more complex quantum systems under full control, perhaps starting with quantum spins, electrons, photons, atomic ions, neutral atoms, and molecules are a new frontier. Whenever a new quantum system was brought under full quantum control, it came with new science and technology opportunities, if you think about it, each of these. And in some sense, I'm just curious to see what will happen when we have some full quantum control over molecules. I should maybe be a bit more specific what I mean by quantum control. So I want to highlight three aspects of what I think contributes to full quantum control. Let's imagine we have an ensemble of quantum systems. These quantum systems can be, several, different things. Could be spins, atoms, molecules, qubits of different kinds. Here I focus just on a two-level system. For simplicity, one aspect of quantum control is that I would be able to initialize this ensemble of quantum systems in a way that each quantum system is in the exact same internal quantum state. That's one aspect. Another aspect is that I would like to be able to change the quantum state of each of these ensemble members in a controlled way. For example, by shining in microwaves or optical radiation, and bring, for example, all of these members of the ensemble to the first excited state. A third aspect is that I would like to be able to engineer correlations between these elements of the ensembles, using interactions between these elements to create correlations or in a quantum way create entanglement. So in general, achieving full quantum control that encompasses all these aspects is non-trivial. One issue is that there are thermal excitations, so when the environment and the system is in contact with a bath at a certain temperature, I can easily have thermal excitation, so I get random population of higher internal states in the ensemble. So one requirement is that I would like to be cold enough, colder than the smallest energy gap of the internal states in the members of this ensemble. So being cold is important. If we look at ensembles that are perhaps specifically made out of atoms or molecules, temperature plays an additional role. Let's look here at a depiction of a gas of atoms or molecules. They have a density of n. In a 3D gas, that relates to the interparticle spacing as density to the power of -1/3. And well, here I show billiard balls, but when we look at it quantumly, we rather should assign wave functions to each particle. The relevant length scale is the de Broglie wavelength, which depends on the temperature as 1 over the square root of the temperature. So when I get colder, the extent of this wave function that describes the particle becomes larger. Okay, so if I get even colder, at some point the wave function is so large that I start overlapping with neighboring wave functions. And that's the interesting point, we call it quantum degeneracy, where I need to take into account the quantum statistics of the particles that I'm dealing with here in my system.
And each of them simultaneously is a two-level system.
No, it's always a multi-level system, right?
Multi-level.
Atoms and molecules have infinite levels.
I'm sorry, another question. You said colder than the level difference in a single atom, or
Right.
colder than the interaction energy between them?
First requirement to get sort of internal quantum state control is that we're colder than the internal energy gaps.
But
As a
can be
first-
hotter than the interaction energy.
Yes, of course. I mean, that is not, if I want to engineer correlations with interactions, then I need to be colder than that as well, of course. So at this point of quantum degeneracy, where the wave functions overlap, there's a difference between fermions and bosons. So fermions obey the Pauli principle, in this very, illustrative way. The particles will try to avoid each other. For bosons, at the contrary, the bosons will like to accumulate in the same macroscopic wave functions. N bosons will accumulate in the same macroscopic matter wave as a Bose-Einstein condensate. And the remarkable thing here is that this corresponds not only to control of internal states. The initial gas already had the internal states of the atoms or molecules controlled. But by having N bosons occupying a macroscopic matter wave, also their motional state is fully controlled and they become indistinguishable. So achieving Bose-Einstein condensate is a way to get full control both over the internal quantum states and the degrees of freedom of motion. So let's look for one more second at this condition of quantum degeneracy. It's where the position uncertainty is comparable to the interparticle spacing. So the Broglie wavelength is comparable to the density to the power of -1/3 for a 3D gas. You can turn this condition into a temperature, and you find that the degeneracy temperature is proportional to the density as density to the power of 2/3. So the lower the density in the quantum system, the lower the degeneracy temperature. And that's something that plays out in nature across a huge range of temperature scales. For quantum degenerate systems, for systems such as neutron stars that are extremely dense, the degeneracy temperature is absurdly high. For systems of lower density, electron gases in metals, the degeneracy temperature is still reasonably high, maybe in the thousands of Kelvin. For the gases that I'm talking about, ultra-cold gases of atoms and molecules, the density is typically less than 1 million times thinner than air. It's an extremely dilute system. So to be quantum degenerate, we need to have sub-microkelvin temperatures. So in some sense, it seems completely absurd to try that. the reason why we still do it is we have the tools to actually do it. So the critical breakthrough on this end was the first observation of Bose-Einstein condensation of atoms. So this happened in 1995. It became possible to accumulate thousands of atoms in the exact same internal quantum state and the same quantum state of motion. So that's, we just celebrated 30 years of BEC. And this result, I mean, when it happened, it infused completely new life into AMO physics, but it had like broad scale consequences. And the reverberations of this result helped us to build quantum simulators based on neutral atoms. It is the reason why we can build ultra precise optical atomic clocks with relying on ultra-cold atomic gases. And the techniques that we have learned since then are the reason behind using neutral atoms for quantum computing. Extremely promising. Let's go back to the history of quantum control. Actually, I cannot get around mentioning I.I. Rabi. Perhaps this field of quantum control started actually with the work of I.I. Rabi. So when he flipped in the late 30s of the last century a nuclear spin with the oscillating magnetic field, it probably was the first time anyone flipped in a more or less controlled way. Spin. And he studied spin flips in lithium, but he actually didn't use atomic lithium, but he used lithium fluoride and lithium chloride molecules, molecular beams. So in some sense, the field of trying to control internal states of molecules is extremely old. It goes back to the beginnings of quantum control. And you may wonder why we're still working on quantum control of molecules. So what did we do for 100 years? Well, the reason is that even simple molecules, such as diatomic molecules, are actually pretty complex in terms of their internal structure. Here's like an energy diagram. This is energy, and this is internuclear distance of the two atoms in a diatomic molecule. You have here this potential well. In this potential well live the vibrational states, the quantized vibrational motions of the atoms in this molecule. So these are the vibrational states, typically spaced by energies on the terahertz scale. On top of that, there is a structure of rotation states, the quantized rotation of the molecule, typically spaced by energies on the gigahertz scale. And then on top of that, you have nuclear spins or hyperfine structure in the molecule, which for typical magnetic fields are spaced by energies on the 100 kilohertz scale. So when you want full quantum control of the molecule, you need to control all of this. Full internal state control. So there's much more than nuclear spins. In practice, we are particularly interested in creating molecules in the internal absolute ground state, in the low vibrational ground state, because on a single molecule level, we cannot decay to lower energy states anymore. So there's no spontaneous decay into lower energy states, so we can hope to have a stable system. So on the theory side, people were intrigued by that for quite a while. The ideas kind of range a broad spectrum, including possibilities to create novel many-body quantum systems, to do quantum simulation of quantum magnetism by using interactions between molecules to emulate spin systems, to study ultra-cold quantum chemistry, to do precision measurements with these molecules. And actually one of the earliest proposals, like here this paper by Dave DeMille, proposed molecules for quantum computing. It was also understood on the theory side that the most interesting molecules to create would be dipolar molecules. Okay, let's remind ourselves how dipolar molecules interact, or how dipoles interact. So dipoles, you can think of bar magnets. They interact with an interaction that goes as 1 over the distance cubed. And then there is an anisotropy, and the anisotropy is such that when two dipoles meet side by side, they repel each other, and when they meet head to tail, they attract each other. So this type of long-range interaction is ideal to create highly entangled many-body quantum states. So this is sort of the correlation part that I mentioned before, if you can control the system sufficiently well. For the experts in the AMO community, or on the side of AMO, you may wonder why study dipolar molecules. There are already other dipolar systems that are under investigation, such as magnetic atoms, which have magnetic dipoles, and ripple atoms, which have extremely strong electric dipoles. So magnetic atoms have relatively weak dipolar interactions. So you're always operating in the weakly interacting regime, while Rydberg atoms have absurdly high dipolar interactions. So in the end, you're basically forced to work in a sort of frozen dipole regime. With dipolar molecules, you're actually in a range of dipolar interactions that it's such that you can tune interactions effectively to tune from the weakly interacting to the strongly interacting regime. That's what makes them particularly interesting. So, you may wonder which dipolar molecule to use. So the first thought is water. It's the most famous polar molecule. The dipole moment is 1.8 dpi. And we know it's pretty nicely controllable in our microwave oven. We apply microwaves and set the molecules in motion, at least in an incoherent way. But it turns out, if you start looking at it, it's actually something we did using some big data tools to understand the spectrum of water. It's very hard to actually laser cool molecules. So we had this dream of writing this paper, a path to ultra-cold water. That doesn't seem very likely. Okay, what else to do? Actually, a door to ultra-cold molecules was propped wide open with a really amazing work of the legendary Debye and Genier at Gila. In 2008, they actually showed that you can first prepare independent ultra-cold atomic gases. They used potassium and rubidium. And first-grade weakly bound molecules of potassium and rubidium, and then use a coherent two-photon transfer process to the rho vibrational ground state to make out of ultra-cold gases of atoms a gas of microkelvin cold molecules. This was a extreme, unbelievable breakthrough on quantum control. And it actually kicked off a wave of research around the world where people started then assembling different types of diatomic molecules. There's a long list by now. And people were actually very optimistic at the time to create truly degenerate gases of molecules. So Debye already showed you can make microkelvin cold gases, which was still above degeneracy temperature.
So can you explain again why cannot you start with molecules and just cool them? Why should you start with atomic gases?
Because you need a cooling technique that can get you to the temperature. And one key technique that gets atoms to the ultra-cold temperatures is laser cooling.
Which is not available for molecules.
It is not, for the vast majority of molecules, it's impossible or completely inefficient. Yeah, that's right. Although there is active research in trying to identify molecules where you can do this, but it's challenging. You're still far from striking range, really like orders of magnitude away from degeneracy. So people made all these different molecules, but it turned out it's unbelievably hard to cool them further, because once you are at microkelvin temperature, the only known technique to get even colder than that is evaporative cooling. So evaporative cooling is something you know from cooling your cup of coffee. You blow the hottest water molecules from above the coffee away, and the remaining coffee is colder. It seems to be a good technique, but you need rethermalization for this to work, and rethermalization require collisions in the sample. What was found experimentally, and actually to this day is not completely understood, which is mind-boggling because the molecules that are involved are actually quite simple. There are inelastic two-body collisions between molecules. They get lost from the sample. When two molecules collide, there's almost unit probability for them to get lost from the sample. It's a process still not understood completely. And because of these fast losses, evaporative cooling wasn't working. So despite being at microkelvin temperatures, you would only need to cool another factor of 10 or so to be degenerate. It didn't work. So that kind of was a big roadblock. So a few years ago, there was sort of the initial signs that maybe something could change here. And what people have worked on is developing techniques for what we call collisional shielding. You want to prevent the molecules from coming so close that they can undergo an inelastic collision. So basically try to develop something that induces a repulsive potential between them before they come close enough to undergo inelastic collision at short range. There was a technique developed by Junier and Gilla that is called resonance shielding, a technique that's called microwave shielding. We'll talk about this in more detail later. That was demonstrated with 2 individual molecules in a tweezer trap in John Doyle's group at Harvard, and microwave shielding in Immanuel Bloch's group in Germany, where they actually were able to create the first degenerate Fermi gas using this technique. With this collisional shielding methods, it became possible to suppress inelastic losses by about a factor of 10. It's not a big reduction. But for fermions, which are sort of already protected by the Pauli principle, 2 fermions don't like to sit close to each other to begin with, so inelastic losses were less of a problem. It became possible to make a degenerate Fermi gas of dipolar molecules. The question that was kind of lingering around was, what about bosonic molecules? It would be great to make a BEC of molecules because you control both the internal state and the external state of motion. The practical issue is the losses are 100 times higher than for fermions. So to actually suppress losses sufficiently well to make a degenerate gas, it would be needed to reduce losses by a factor of 100 to 1,000 compared to the unprotected, unshielded molecular gas. So there would have to be a huge factor gained between the state of the art and what would be necessary to make a BEC. But the first part is you need the bosonic molecule to make progress on this. So this is where our experiment comes in. We use in our experiment sodium-cesium molecules. Sodium-cesium has a dipole moment of 4.60 pi, so this is even 3 times more than water. It's a highly dipolar molecule. And when you turn this dipole moment into an interaction length scale, we call it the dipolar length, then you find that that length scale can be tens of micrometers. And typically interparticle spacings in our systems are on the order of a micrometer. So you already see that there should be a way to get into the strongly interacting regime with this molecule. So let's get into the details of how we actually make this. So this is the effort we drove forward over the last couple of years at Columbia University. There's a lot of steps involved. I will try to give you a brief overview of what it takes. So the first step is to actually create these molecules to begin with. First, we start with microkelvin cold overlapping ultracold gases of sodium and cesium. Then we make weakly bound molecules of sodium and cesium. Then we transfer them to the absolute internal ground state. Okay, so this started about 8 years ago at Columbia University in an empty lab. We built laser systems for laser cooling of sodium and cesium. So this is like about 5 feet across, so just full scale. Then this laser light is transferred via optical fibers to an ultra-high vacuum chamber in which all this cooling happens. And after we assembled all of this, the first step was to make overlapping gases of sodium and cesium. So we actually, for the first time, made overlapping BECs of 2 alkali atoms, which is actually a very interesting system in itself. 2 overlapping superfluids. That might be an interesting field of study. But we pushed on to make weakly bound sodium-cesium molecules. For that, we use a technique that's called Feshbach resonance. That is, in simple terms, sort of a gateway into the quantum mechanically least bound vibrational state that a molecule can have.
Sorry, what are all those colorful little things?
This
like
is
lenses,
mirror mounts and
mirrors?
lenses, yeah. And other optics elements, yeah. Wave plates, all kinds of stuff.
And you need hundreds of those?
Yeah. That's what happens. Yeah.
Thousands?
Yeah, on the order of 1,000. I didn't show you everything, there's another table. Yeah. So then we have weakly bound molecules, and then we do a coherent 2-photon transfer process, similar to what Debbie pioneered 15, 20 years ago, to transfer the molecules into the absolute internal ground state. It's a fully coherent process that's reversible, and we can do it with 90% efficiency. So what do we have at this point? We have a gas of 10,000ths of our sodium-cesium molecules at a microkelvin temperature, where all molecules are in the exact same internal quantum state, specifically the rho vibrational ground state. So we have full internal quantum state control. It's a near degenerate gas. So now we want to push forward on cooling this gas further. Turns out a key technique is microwave control of this molecule. So what's going on here? When we initially create the molecule, we prepare it in the vibrational ground state, but also in the rotational ground state. The quantum number we denote as J equals 0. And the first rotationally excited state of the molecule is it's like 3.5 gigahertz away, and there's essentially 3 possible transitions: a sigma plus, a pi, or the sigma minus microwave transition. It turns out for sodium, potassium, these states are almost degenerate. They are within a few kilohertz of energy, so it was clear for us early on that we need to build a microwave system that can independently address these different transitions selected by polarization. For that, we developed a new type of antenna that can produce extremely clean circularly polarized microwave fields. We call it, for obvious reasons, a cloverleaf antenna. So there's 4 independent loops that are independently controlled and can generate extremely clean circularly polarized microwave field. Ellipticity that we measure on bench tests is 2 degrees, but actually it's a lot better. We can use the molecules to probe this, and it might be the most cleanly circular polarized microwave field ever created. This antenna is integrated into the vacuum chamber. This is about 2 centimeters of scale in between these viewports of the vacuum chamber, and the molecules are in between here. So we can use this antenna to selectively address the sigma minus and the sigma plus microwave transitions and drive Rabi oscillations between these 2 states. And we find that a Rabi coupling of more than 40 megahertz. So it's extremely, very strong coupling. If you look at that in a quantum information language, it means then you can drive a pi over 2 pulse or a Hadamard gate in 6 nanoseconds. That's reasonably fast. But what's more important is in these molecules, it's not shown in our lab, but colleagues in the UK have just in last year demonstrated that you can reach a coherence time on these rotational states of more than a minute. So you can drive a 6 nanosecond gate, single qubit gate, and have a coherence time of a minute. So you can conceivably accommodate 10 billion gates in the coherence time. It's most likely the highest ratio in any system. So this is very promising also for quantum information. It's not what we are currently focused on. So let's focus on actually cooling the system further. So how do we use the microwaves for cooling? We actually apply the microwave off-resonantly, the sigma plus microwave, and do what we call microwave dressing. We basically mix the rotational ground state with this first rotationally excited state here. And on the theory side, it was worked out that if you do that, you can modify the collisional potential between the molecules. In a classical picture, what's happening is this circularly polarized microwave field sets these dipoles of the molecule in rotation. And when this is happening in a quantum, in a microwave dressed way, you can actually achieve a situation where these dipoles that are rotating repel each other no matter in which direction they meet each other. So let's discuss this for 1 more minute. When you have rotating dipoles and they meet like on the vertical axis and they rotate in sync, they will always repel each other because it's an effective side-by-side interaction. When the dipoles are meeting in the horizontal plane, well, then you need to be a bit more careful. When the dipoles are aligned like this in one moment in time, they attract each other. When they rotate by another 90 degrees, they actually repel each other. And then you have a time average potential that you need to consider. Turns out when you do the time averaging, it's actually attractive interaction. So they first attract each other when they meet in the horizontal plane. But when you do this microwave dressing correctly, you can induce a situation that when the molecules come closer to each other, the dipole-dipole interaction admixes other internal states that effectively lead to a reorientation of this molecular rotation, and they rotate side by side again. This sounds like pure magic. This was proposed theoretically about 10 years ago and was treated like something obscure until someone tried it. And lo and behold, it actually works. So the interaction potential of these microwave dressed molecules is such that there's very weak long range interaction for beginners, and then there is a repulsive shield. Okay, we applied that to our system and studied what the impact of this shielding is on the lifetime of the molecular sample. When we do nothing, the molecular gas, at this microkelvin temperature lives for like a little bit more than 10 milliseconds. When we do this microwave shielding, the lifetime goes up by a factor of 50. The second scale lifetime, which in the field of...
What exactly does it mean that it lives for a short time? You form some bound molecules?
These inelastic collisions lead to
to what?
Molecular complexes.
Complexes, okay.
What
they are no longer individual molecules.
That's right. But what precisely happens is actually not yet understood. It must be some form of complex, but on the quantum chemistry level,
detector of molecules tells you molecules are no longer.
We only
there.
see individual molecules.
Okay.
You cannot detect complexes. That's right. Okay, so enhancement of 50 sounds good, but remember. I said before, we need to get like a factor of 100 to 1,000 improvement. So we are away from that. And indeed, cooling was not very efficient, not efficient enough in that scenario to reach a BEC. It turned out this microwave shielding suppresses 2 body losses, but it opens a channel for 3 body losses because there's a little bit of an attractive potential well before the interactions become repulsive. When this well is deep enough, there can be a bound state, and when you have a bound state, you can have a 3-body collision where 2 molecules end up in the bound state and the other one carries away the excess energy. That was a process no one had on the radar in this kind of setup, and we figured that out sort of experimentally and later modeled it together with Chris Green from Purdue, who is an expert on 3-body collisions and found extremely good agreement. So solving this 3-body loss problem, in addition to the 2-body loss problem, was key to achieving a Bose-Einstein condensate of our molecules, of molecules, period. So what is the current setup? So we have our microkelvin cold gas of molecules in an optical dipole trap, so it's intense laser beams that hold the sample in the vacuum chamber, and they are exposed to this rotating microwave field. And the issue is that there is some attractive potential that kind of induces then these 3-body bound states. So how can we solve this issue of attractive potential? And this attractive potential comes exactly from what I sort of classically explained earlier. The rotating dipoles that meet in the horizontal plane, they first attract each other before they become repulsive. So we kind of need to counteract this attractive potential. So how could we do that? Well, the intuitive picture was, how about we add another microwave field here, dress on this pi transition? What does a pi microwave field do? Well, it induces dipoles that oscillate like that. The circular does this, and the pi does this. And by simultaneously dressing the molecules, maybe I can engineer a collisional potential that gets rid of my bound state problem. And lo and behold, with our close collaborator Thijs Karman, we theoretically analyzed this situation and found we can engineer a collisional potential between these molecules that's flat, and then becomes deeply repulsive. We basically make hardcore bosons out of our molecules. So just to illustrate that to you in terms of scale, our molecule is 8 Bohr radii in size, and this repulsive shield that we make with our microwave field has a radius of 2,000 Bohr radii. So this picture is 2-scale. This is a 2-scale illustration. So we make out of a tiny molecule a pretty big ball. In this scenario, we then do evaporative cooling. And we do it in a way that we trap the atoms the molecules in this trap. And the hottest molecules we remove just by lowering the intensity, the depth of this trap. And with that, the hottest molecules go away and we get rethermalization. And hopefully we get colder. Okay, we do this on the time scale of a few seconds. So what do we see in the experiment? Initially, we start with microkelvin temperature. It was already very encouraging to see that we can get down to 40 nanokelvin. When we look at the cloud, the density distribution of the molecular cloud at 40 nanokelvin, we still can fit this with a Gaussian, which indicates to us that this is a thermal gas. When we cool further, we see that this density distribution of the molecules, to be precise, that's actually the momentum distribution of the molecules. You see that the peak grows out of this Gaussian center that becomes more and more pronounced. That is the indication of populating the macroscopic wave function, the formation of a BEC. So we see here BEC fractions up to 60%. That's the very first time a phase transition was crossed with an ultra-cold molecular gas. That was a big moment in the lab. That's actually not a stage picture. That's on the evening where it happened. So that's a little bit more than 2 years ago. And what we did in practice here was that we started with a gas at 700 nanokelvin by evaporatively cooling it by lowering the depths of the trap. We lowered the temperature in the end all the way down to 6 nanokelvin. And the phase-space density increased rapidly. What is phase-space density? Phase-space density is a measure for the ratio of the de Broglie wavelengths and the interparticle spacing that I was talking about earlier. And when this ratio reached approximately 1, you cross the BEC. So our cooling here was like 100 times more effective than anything that had been seen before. It's important to note, sort of, for the experts, to make a BEC, you actually need to work in the limit of a weakly interacting gas. When you have strong interactions in your gas, you actually get quantum depletion. Interactions populate, induce population of quantum states that are not your ground state, and you don't get a BEC. That's, for example, the reason why it's challenging to make a BEC of hydrogen. Interactions there are always relatively strong. So in our case, we have interparticle spacings on the order of a microkelvin, but the interaction length scales, the dipolar lengths and the scattering lengths in our system are on the order of less than 0.1 micrometer. So this is still a weakly interacting gas, although at the core the molecules are dipolar, with this trick of combining the sigma microwaves and the pi microwaves. I switched off the dipolar long-range interactions for beginners. So I make basically just a hardcore boson gas. So we made a BEC of hardcore bosons with minimal dipolar interactions. Also, the lifetime of this BEC is very long, more than a second. So we suppressed losses in the end, not by a factor of 100 or 1,000, but actually by a factor of 10,000. So it works much better than ever imagined. Lots of excitement when this came out. In the meantime, we can also, make BECs that have a lot more molecules in them than before. We make now BECs with several thousand molecules. Before we had maybe a few hundred molecules, which allows us then to take this, high resolution images of the BECs and, assemble this famous trio of pictures that made BECs quite famous. Okay, so let's get a little bit to the exploring part of this BEC. And one important aspect is, what happens actually when we switch on dipolar interactions again. I told you in the beginning, we're interested in dipolar interactions. And just a minute ago, I told you to make a BEC, we switch off the dipolar interactions. So what's going on when the interactions come back? And one concern was when the interactions come back, the losses come back too. So we try to understand what happens when we increase the dipolar interactions again, what happens to the losses. So the setting is as described before. We have our molecular gas and we have our two microwave dressing fields, the circularly polarized and the pi polarized one. By changing the balance of these two dressing fields, we can have the system being dominantly interacting with dipolar interactions, basically your standard interaction of bar magnets. But you can also have, when the sigma dressing dominates, you can have the interaction of rotating dipoles dominate. We start calling that anti-dipolar interactions, the dipolar interactions with the overall minus sign. You will say maybe that's kind of a trivial minus sign that has no consequences for the physics. However, in a 3D system, this minus sign can have profound impact on the many-body behavior. Anyway, so what we study is basically, by controlling these microwave fields, we have a very fine control knob about of how strong effectively the dipolar interactions are. The BEC we initially make by tuning this microwave dressing such that the dipolar length, which is plotted here, is effectively 0. By imbalancing these microwave fields, I can go either dipolar or anti-dipolar and get extremely controllable interactions. Question is, what happens to the losses? And without going into too much detail, we find that the losses, and what I plot here is 3-body losses, remain extremely suppressed in a broad window of interactions. In practice, this window of extremely suppressed losses corresponds to a tunable range of dipole lengths from 0 to 20,000 Bohr radii. So I have a really large tuning range that really carries me from weak interactions to strong interactions. Before, at some point, losses take over again. This is exactly when the collisional potential is attractive enough to support a bound state. So we actually fully understand on which scenarios we get losses and in which scenarios we can suppress losses completely. We actually suppress 2 and 3 body losses below our detection limit. That's something that's not even possible in ultra-cold atomic gases. Turns out if you put together the number, this tuning of interactions allows us to enter the strongly interacting regime. So here we do this sort of theoretically, the discussion. We consider the achievable ratio of dipolar interactions and kinetic energy, and for the parameters that we measure in terms of loss suppression and achievable density and achievable dipole moment, we can explore this range that can be reached and find that this interaction parameter can be continuously tuned from 0 to 7. So when it's above 1, you would say you're on the strongly interacting regime. So really what I told you before, molecules offer a way to go from weak to strong interactions. That's sort of what I mean. Still, we haven't applied these interactions to a BEC yet. These measurements on the loss rates here we did with a thermal gas. So what happens when I throw these interactions on a BEC? Okay, I should mention we do the interaction tuning in this case for the data I show you on the following in a slightly different way. I told you we can tune from dipolar to anti-dipolar interactions by tuning this coupling of the microwave dressing. It turns out there's another knob that can be used, which is we can change the degree of ellipticity of the circular microwave field. With that, we can induce dipolar interactions that break axial symmetry. So when 2 bar magnets interact, there is axial symmetry to this interaction. With this ellipticity tuning of the microwave field, which induces then sort of an elliptical pattern of dipolar interactions, we can create a new type of dipolar interactions that is still decaying as 1 over r cubed, but has a different anisotropy. We did that because it's actually something that has never been done before, so it's a new type of dipolar interactions, and it's very tunable. It's experimentally very nicely tunable with a microwave ellipticity. So it turns out basically that the dipolar interactions are a linear function of the microwave ellipticity. So it's very nice.
Quadrupolar dipole.
Quadrupolar dipole. I don't, it's still a dipolar interaction in the sense that it decays as 1 over r cubed. So so we call it non-axially symmetric.
Oh, it is still 1 over. So you can arrange for 1 over cubed and yet y2.
Y2 2, exactly. Yeah, that's a new thing. That's possible through this tuning.
Because of your funny motions
microwave
of molecules.
Okay. That's right. We can also do traditional dipolar and antidipolar interaction. I will show you a little bit later. So what happens now to the gas, to the BEC when we do that? Let's study the molecular gas as a function of time of flight expansion. So first we create a cold molecular gas in the trap, and then we release the trap, and look how the gas expands as a function of flight time. We first do this with a BEC. At ellipticity 0 is where we make a BEC. A BEC expands slowly but surely. So initially you have a small cloud, and because the kinetic energy is very low, it slowly expands, but it still expands. When we induce dipolar interactions, we actually see the cloud changes shape. We see something that we call electrostriction. When we increase the strength of the dipolar interactions even further, we see that the BEC shrinks quite dramatically, and then the cloud itself doesn't expand anymore in time of flight. That's a self-bound droplet. We can change the axial orientation of the dipolar interactions by 90 degrees. And actually, since our trapping potential is a little bit elliptical, that changes conditions such that the BEC even breaks up into arrays of individual droplets. And these individual droplets don't expand anymore. They are also self-bound. And you see that in time of flight, these droplets repel each other due to dipolar interactions.
So the most strongly confined BECs look like they have a halo around them. Is that an optical diffraction effect?
Yeah,
or is
that's
real?
from the imaging.
Okay.
These droplets are much smaller than we can resolve. That's an airy disk from the imaging. Yeah, excellent question. Thanks. So these are very, very dense systems. Already clear just from looking at that they are much smaller than the imaging resolution. So this is an interesting state. For example, for these arrays of droplets, an interesting question is there phase coherence between these individual droplets, which then would be a situation that often is described as supersolidity, where you have a density modulation and phase coherence. That's something we're currently investigating. Another question is how to actually model these dipolar molecular systems. It turns out in the field of magnetic atoms, what had been very successful to understand weakly interacting, weakly dipolar many-body systems was to apply what goes under the name extended Gross-Pidaevsky equation. It's a Gross-Pidaevsky equation that includes a dipolar term, interaction term, and then includes a first order beyond mean field correction, the Li-Huang-Yang correction, that explains the stabilization of droplets in weakly dipolar systems. It turns out, however, in our system, the dipolar interactions are so strong that here this integral that's behind this G LHY factor has a significant imaginary component, so this becomes very unphysical, and it's an open question how to actually describe this strongly dipolar system that gives rise to the droplets. So that's an ongoing theoretical quest. Quantum Monte Carlo people are extremely interested in this system by now. But we approach this for now from the experimental perspective. For example, we asked the question, how dense is really this dense droplet? And we figured out a way how to measure the density. The BEC has a density of 10 to the 12 particles per cubic centimeter. And we measure that in this tightly bound droplet, the density goes up by a factor of 100 compared to the BEC. It's a very dramatic change. There's also here quite an edge, so that looks like a phase transition. This density comes with a couple of consequences. One is due to this high density, the ratio of interaction energy to kinetic energy is about 4. So this is presumably the first time a strongly dipolar ultracold gas was created. Another interesting aspect is this density is very close to the maximum density that is allowed by the hardcore radius that we induce with our microwave dressing. So that, I showed you this illustration of, the big molecules, the molecules, we have this large shielding radius. This sets a maximum density that you can conceive. And the density that we measure here is very close to the maximum density allowed by the hardcore diameter of the particle. So it's an interesting question, what the quantum state in this dense droplet actually is. Is it still a superfluid? Is it a quantum liquid? Is it perhaps even a crystalline state? We don't know. These are interesting scientific questions. Okay, so with this, let me give you a bit of an outlook. So based on what we see, I think we can say that these molecular systems are a new modality for many-body quantum systems. The power of these systems comes from the fact that we can engineer the collisional potential extremely flexibly. We can tune the hardcore radius. We can tune the strength of long-range dipolar interactions with the location of this bound state that I mentioned. We can also tune, in addition, a scattering resonance. And this is all microwave control, so we can do that on very fast timescales. So, for example, you can imagine we have a gas with some interaction radius or with some gas parameter. And then with the microwaves, we can snap on a gas parameter that is much larger. So we can go from a sort of ideal quantum gas to quantum van der Waals gas. And that's a very interesting question. What are the thermodynamic consequences of a finite size radius in a quantum gas? That's actually, as far as I can tell, a scenario that's not very well understood. while classical van der Waals gases are something we discussed in the classroom. So it will be interesting to study more the 3D behavior of these gases. These droplets that I showed you, currently we cannot resolve the shape, but quantum Monte Carlo simulations indicate that these droplets do not have to be round. They might have be disks or other shapes. It will be fun to also put this dipole into two dipoles into 2D. Early proposals go back almost 20 years ago of putting molecular dipoles into D and study the phi-phase diagram. For weakly dipole interaction, you should get a superfluid into D, but when the interaction becomes strong enough, you should see a crystallization transition, basically a dipolar analog of a Wigner crystal. And then the interesting aspect is that we should be able to create such crystals in a regime where the intermolecular spacing is big enough that we can, in a quantum gas microscope, resolve each and every molecule. So you study really formation and dynamics in a crystal sort of in real time. There's actually an interesting connection of these ideas with recent work in 2D quantum materials, especially in Jishan's Kinfei Max Lab and also Corridin and XYZ at Columbia, studying excitons and bilayer 2D quantum materials. So basically electron hole pairs that are in two layers. Well, electron hole pairs are dipoles also. Clearly there's a lot of overlap. It will be really interesting to understand how close, similar or dissimilar these two systems are in terms of the physics. We are actually also very interested in putting these molecules on optical lattices. This opens a door to study extended Hubbard models with long-range interactions. Interesting Mott insulator phases with fractional filling are predicted for this. Would be great to see that. And with molecules, with unit-filled arrays of molecules, it could be actually possible to study quantum magnetism in interesting regimes. So I want to just take 2 minutes to highlight, completely switch gears and highlight another project in our lab, which is on atomic tweezer arrays of strontium. With the students, I talked a ton about this already, but I want to highlight this very briefly here. Atomic tweezer arrays have become a really powerful platform for quantum simulation, quantum computing. It is a way, besides making BECs, to control internal and quantum states of motions of atoms completely. You can make arrays of individual atoms, so each dot here is exactly one atom. That's used for quantum computing, quantum simulation. Turns out also a very interesting platform for tweezer clocks. Typical array sizes are on the order of 1,000 atoms. In our lab, we are interested in these aspects, but we are also working closely with our friend and colleague Ana Senio Garcia on realizing atomic arrays that can display super and subradiance, cooperative emission effects between the atoms. To see such a thing, you want to have the atoms closer to each other than the emission wavelengths. That's actually a challenge. Typical emission wavelengths are on the micrometer scale, and typical array distances of atoms in arrays are on the order of a few micrometers, so that's kind of challenging. But we figured out a transition in strontium that is in the mid-infrared range, about 3 micrometers, and that opens the door to get to sub-wavelength arrays. That's how the lab looks. To make the tweezer arrays, we actually have a very fruitful collaboration with our friend and colleague Nanfang Yu. We develop a new way to make tweezer arrays using holographic metasurface. You shine a laser from one side. The metasurface turns that laser into an array of tweezer traps, which can hold a single atom. That's a nanofabricated device with a lot of new possibilities compared to state-of-the-art standard techniques. This is a result that just came out in Nature 1 or 2 weeks ago, where we show actually the first trapping in metasurface generated arrays of atoms. These are different array structures of strontium atoms trapped in these arrays. We can detect and prepare single atoms in these arrays. And importantly, these metasurfaces open a way to really scale the size of tweezer arrays. So I told you before, typically 1,000 traps. At this point, with metasurfaces, there's a path to more than 100,000 traps. We wrote the paper showing single atom preparation in these metasurface array, and then we had a theory discussion where we said we can, on principle, make 100,000 traps. The referees got back and said, "Great paper, show me the 100,000 traps." Well, we got a little bit worried whether that actually will work, but then we did it. So here you see a video of a tweezer array, a 600 by 600 tweezer array. Here you zoom in into the 30 by 30 range. That's sort of the current state of the art, and that's what we are looking at here. So that's a huge boost over the current state of the art. We can also scan across this. This video takes a minute, and Javad will kill me if I show the entire video. So why do we care about larger arrays? Well, larger arrays will be good for making atomic arrays with more logical qubits. It will be good for quantum simulation in these arrays, as it reduces finite size effects. And if tweezer arrays are used for clocks, the increase in atom number in these arrays should lead to a significant improvement of clock precision. In terms of pushing towards these long wavelengths quantum optics, we've also made very good progress. We actually have control over this 2.9 micrometer transition in our strontium atoms. We have a laser with kilohertz line widths, and we do spectroscopy on tweezer trapped atoms on this transition for the first time, and we observe this transition with kilohertz resolution. So we're kind of at the verge of pushing that into interesting regimes where you may see cooperative emission effects. So with that, I'm going to skip to the summary. I'll focus on the molecules. So I showed you the creation of a BEC of molecules. I showed you the next steps towards quantum strongly interacting dipolar many body systems. I want to highlight a few take-home messages. So I think we have reached a level of control over molecules that we can say it's a level of control that's similar and actually in some aspects higher than for atoms. We have real-time control over the collisions and interactions of the molecules, and we see new quantum liquid behavior. So it's a very interesting juncture in this field of ultracold molecules. For decades, people have struggled getting these under control, and now it will be interesting to see how we can study that on the level of many body physics, perhaps at a later stage also on the level of single molecule control and quantum computing opportunities with the system. I want to highlight the great work of the team. For the molecule effort, Ian Stevenson played a huge role. He's now faculty at the University of Virginia. We had an amazingly strong generation of first students building up the experiment. Nicolo is still in the region working for with Connect. Next generation of students is Wei-Jin Yuan and Siwei Chang, who are about to graduate, and then the next generation of students, Hanel Kwa, and Asaf Toprachi, and the postdoc Lin Su, who just came from Harvard to us. And on the tweezer experiment, I want to highlight the amazing work of Aaron Hullman, first generation student, and Shimo Sun, who is amazingly strong student working on this, taking this to the next level. Also want to thank the numerous collaborators on both projects, funding agencies, and you're always interested in motivated, probably here mostly important postdocs, so reach out if you're interested. Apply to Columbia. Thanks so much. Thank you.
Beautiful talk. Thank you, Sebastian. Any questions? I have some really hard ones.
Can I ask a little one? So of course dipole-dipole interaction is always Y2. I said something.
It's always Y2, yes.
Always Y2, so I said something stupid.
Yeah.
But the question
It's
is
Y20 usually.
right, but why is it in one case one Y20 and another Y22? What makes this difference?
So this is because we this is actually crashing right now, so we just made it in time.
Maybe I stood out. Sabotage.
So we do we induce this by inducing simultaneously a vertically oscillating dipole in the molecule and a rotating dipole. But the rotating dipole doesn't rotate perfectly circularly, but wobbles a bit. We induce it in an elliptical way. And with this, we break axial symmetry that would be usual for a Y20 interaction. So we get
So
strong
if they were perfectly aligned, it would have been Y.
Y20. So actually, what I showed you before is actually, it's all Y20. I showed this paper. We kind of, we use this Y22 interaction because it's something new, something interesting. I thought I had a slide in the talk where I show you. We see also droplets.
But this requires that they be not aligned.
They are aligned. They need to be perfectly aligned, but one is elliptical. One microwave field is elliptical, not round.
Okay.
That is what breaks the axial symmetry.
Okay.
We see also, I thought I had a slide in there of preliminary data, but we actually see also droplet formation for dipolar and anti-dipolar interaction. It's a whole zoology of droplets. Crazy stuff is happening.
Okay.
It's still preliminary.
Chris?
Is this two-photon process that you use to go from the atomic gases to the
Right.
molecular gas? Is that a generic process that can be used for basically any two-atom system, or is that specifically, like experimentally, in terms of experimental feasibility, I guess? Is this something that you can use for any system, or is it just
Right.
really for this?
So far, people have found for any two atoms that they have tried, they have found a pathway to the ground state. Sometimes it requires molecular spectroscopy because you need to find an excited state that you kind of go through.
Okay.
But it's a very general scheme. It's called stimulated Raman adiabatic passage. Styrap, Klaus Bergmann in Germany developed it in the 80s and 90s for microwave transitions in atoms. It's a coherent transfer scheme that works for any three-level system.
Got it. Okay, thank you.
So one question I have. So now that you can do everything, what about the spin and the spin orbit? I remember I had seen this spin orbit paper from, I think, Martin's group, maybe?
Yeah.
Is it possible to find a molecule that, I mean, I know it is already complicated, but
Yeah.
is there any path there? Or?
Yeah, so there is actually some, it's not something we are actively now working on, but on the theory side, there are a number of proposals now how to engineer spin orbit coupling and kind of, have a.
Is it more like a heavier molecule, or is it more
No,
like
it's more about the engineering of the interactions. You can kind of induce a momentum dependence in the interactions in a way, and
to get the two parabolas, basically.
right, and that's something theorists think about. I have not thought too much about practically implementing it because this system is already so absurdly rich. You're just trying to get it. This is really so. It's a pretty interesting situation right now. In cold atoms, I mean, for many years, I've been in this field now for since the early days of my undergrad. I mean, we rightfully got the criticism sometimes that we're just measuring data that was kind of predicted by theorists anyways. But here now in this system, this is like we're in discovery mode. I mean, basically the experiment tells us what's interesting, and that's a really new situation.
You made it messy enough so that theories can no longer.
Well, but in a very controlled way. For we know exactly what's good is we know exactly the collisional potential, so you can feed that into, let's say, quantum Monte Carlo code and actually make progress. So it's not so messy that we don't know what's going on. We actually know on the microscopic level what's going on. But what the consequences are on the many-body level, that's actually interesting.
In condensed matter, we are really good at that.
Yeah, right.
Anyway, so if we go downstairs for some wine and cheese, I will
Sounds good.
continue the discussion. Let's thank Sebastian.